bifurcation limit. Now, we develop the model. First, Almanja et al. Assume the p-diffuse as a self-limiting and monotonically increasing function alpha x by x plus beta. And the discrete time of this analog model 23 is the discrete time model is like this. This is the parameter value. Now we analyze the model 24. We first find the equilibrium boundary equilibrium point. There we get two equilibrium points. One is at the origin E0 and one is axial E1 K0 and is the interior equilibrium point where the interior equilibrium positivity is tested by minus C plus P X star into 1 minus extra plus alpha star extra plus B greater than 0 and C and X star less than P. Now, to find the nature of the load in the neighborhood of the equilibrium point, so we write the Jacobian matrix of the system 24 is 26 from the Jacobian matrix. We try to find the behavior, local behavior of the near the equilibrium point. In the E0, 0 point is always saddle point and E1, K0 is the stable if and only if the following condition hold. Last lecture, how can we find the stability criteria? You know, the lambda 1 and lambda 2 eigenvalue if less than 1 in the system is stable, otherwise not. And from this consideration, we get E1, K0 is stable if R lies between 0 and 1 and C greater than the parametric value. And the interior equilibrium stable if and only if Schur-Cohn criteria. Last day I told about the Schur-Cohn criteria. What is the Schur-Cohn criteria? If the system is stable of that equilibrium point, if case of the Jacobian, mod of case of Jacobian minus 1 is less than the determinate value of the Jacobian less than 1, then the system of stable. That's why I written first term is mod value is space minus 1 less than determinate value of the Jacobian at the point x star y star is less than 1. Now we find the equilibrium point at which Neimark-Sacker bifurcation following condition are satisfied. In continuous model system, we find also bifurcation theory, and here is the another theory is Neimark-Sacker bifurcation. And we get in the system that the system has a pure coupling bifurcation by the following condition. And we study the global stability of the system, and this is the following condition. And go to now in the numerical result, putting the same value of the parameter value and change the sum one to get the following diagram. First diagram is the bifurcation diagram for plate period population. Parameter alpha lies between 0.1 and 2. This is the numerical maximum Lyapunov exponent. The line, the scatter line below this line give the bifurcation. These are numerical simulation result of this model. We get at the point alpha equal to 1.9, we get a limit cycle, but when the value of alpha is increased, the system is stable. These are following the basic portrait bifurcation with respect to R. First we define the bifurcation theory with respect to alpha, and now with respect to R, that is both term. This is the numerical simulation to find a bifurcation analysis. This is the Lyapunov exponent. This is the following result. Base portrait for different value of R bifurcation diagram of the prey and predator population of the system with respect to the parameter is the maximum Lyapunov exponent for H, and for the value of H is 0.6 is limit cycle. When it increases, the system is stable. Is the stability nature of the system for a different initial point where is written 0.1, 0.9, 1, 0.7 and others. Now, I go to the discussion part. See, if the pay growth rate lies in a certain interval, as well as the death rate of the predator population is higher than a threshold value, then the predator population go to extinction and the prey population approaches environmental carrying capacity. If the condition is sufficiently stable coexistence, both prey and there is a global stability condition, and the system is growing in condition holds, note that the intrinsic growth rate of the prey required to below the threshold value 1 for the system to achieve global stability. The maximum reduced capacity of the prey, earlier we have shown the result, 1.6 is stable, has a stability, because it affect the dynamical system, otherwise it is limit cycle. Small amount of prey reduced do not affect the chaotic behavior, but significant amount transform chaotic behavior into oscillatory behavior and eventually stable fixed point. And in the result of R, that is intrinsic growth rate of prey, increase the interior fixed point of the system, loses its stability, and this system becomes periodic. If we increase R even further, the system eventually generates into chaos. You have already seen in figure 9. Interspecific competition of the predator prey stabilize the system. Increasing age dampen the oscillatory behavior that make the system locally isolated stable to a fixed point theory, Neimark-Sacker bifurcation. This the following is the references, and this paper is published in the mathematical method in the applied sciences, and this is the references in the paper already published in 23. Thank you.